These are the answers to the AP Chemistry packet that covers topics 4.5 and 4.6. On this slide, you can see Unit 4 at a glance. Unit 4 is entitled Chemical Reactions. In this video, we'll take a look at topic 4.5, Stoichiometry, and topic 4.6, Introduction to Titration. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 4.5, Stoichiometry. Here are some essential knowledge statements from the AP Chemistry course and exam description. Because atoms must be conserved during a chemical process, it is possible to calculate product amounts by using known reactant amounts, or to calculate reactant amounts given known product amounts. Coefficients of balanced chemical equations contain information regarding the proportionality of the amounts of substances involved in the reaction. These values can be used in chemical calculations involving the mole concept. Stoichiometric calculations can be combined with the ideal gas law and calculations involving molarity to quantitatively study gases and solutions. Question 1. Ammonia, NH3, reacts with oxygen gas, O2, to produce nitrogen monoxide and water vapor, according to the chemical equation shown above. Part A. Calculate the number of moles of O2 that is required to react completely with 28.3 moles of NH3 in this chemical reaction. So we'll start with the coefficients that we have in the balanced chemical equation. The 4, the 5, the 4, and the 6, they represent mole ratios. We don't need to use the periodic table for part A. We're simply converting moles of one chemical to moles of another. So we'll write down 28.3 moles of NH3, and we need a conversion factor that puts the units moles of NH3 on the bottom and moles of O2, which is what we're trying to find, on the top. So it's going to be 5 moles of O2 for every 4 moles of NH3. So we do that math, 28.3 times 5 divided by 4. Here is our unrounded answer. And since 28.3 has 3 significant figures, we will round off our final answer to 3 significant figures. That makes it 35.4 moles of O2. Part B says to calculate the mass in grams of NH3 that is required to react completely with 175 grams of O2. So now for part B, we do need to consult the periodic table, because not only will we have to convert from moles of one chemical to moles of another using the coefficients in the balanced equation, but if we have to convert from grams to moles or moles to grams, we need the molar mass. And that calculation comes from the information on the periodic table. So for NH3, the molar mass of NH3 is 17.034 grams per mole. Again, there's 1 nitrogen and 3 hydrogens. Those are the atomic masses of those elements. We just added those up. And then for O2, it would be not 16, but rather 32. So 16 times 2, 32 grams per mole for the molar mass of O2. We were given 175 grams of O2. So our first step will be to convert from grams of O2 into moles using the molar mass. So grams on the bottom, moles on top. Now we're going to convert from moles of O2 into moles of NH3 using the coefficients. So there are 4 moles of NH3 for every 5 moles of O2. And then back to grams using the molar mass of NH3, that would be 17.034 grams of NH3 for every 1 mole of that compound. If we start with the left and go from left to right, 175 divided by 32 times 4 divided by 5 times 17.034. Here is our unrounded answer. And since 175 grams, which is the measurement that we started with, has 3 significant figures, we'll round off our final answer to 3 sig figs, so 74.5 grams of NH3. Okay, before moving on to question 2, I just want to talk briefly about the concept of a limiting reactant. The limiting reactant in a chemical reaction is the reactant that is completely consumed when the chemical reaction is completed. The limiting reactant determines the maximum amount of product that can be produced, which is known as the theoretical yield. This particular example question is not from the current packet. It's from the previous packet, the one that I talked about in the video for topics 4.1 to 4.4. Topic 4.3 is entitled Representations of Reactions, and here we see a balanced equation between nitrogen and hydrogen to produce ammonia, NH3, and we see a particle diagram on the left representing the reactant mixture, which contains 4 molecules of N2, indicated by the black circles, and 6 molecules of H2, indicated by the white circles. With respect to the limiting reactant, until we really process this information, we don't know what the limiting reactant is. Let's take a look. In the balanced equation, for every 1 molecule of N2 that reacts with 3 molecules of H2, 2 molecules of NH3 are produced. If we have an additional molecule of nitrogen reacting with 3 molecules of hydrogen, we get 2 additional molecules of NH3. But if you look closely in the particle diagram on the left, you realize that there's no more white circles that have not been reacted in terms of this process. There are 2 molecules of N2 that are still remaining as leftover at the end of the reaction. So the limiting reactant, the one that was completely consumed in this example, was the hydrogen, and the excess reactant was the nitrogen. The limiting reactant, the hydrogen, limits the theoretical yield, or the amount of product that can be produced. So 4 molecules of NH3 were produced in this example, which came from complete consumption of the limiting reactant, hydrogen. All right, now we can move on to question 2, which again, we're going to be talking about limiting reactants a little bit more. Equimolar amounts of CH3OH and O2 are introduced into a rigid, previously evacuated reaction vessel. The mixture is sparked, and a chemical reaction occurs according to the equation shown above, until one of the reactants is completely consumed. Which substance, CH3OH, which is known as methanol, or O2, oxygen, is used up completely in this experiment? Justify your answer. Equimolar just means equal number of moles. So let's pretend that we have 2 moles of each reactant, 2 moles of methanol and 2 moles of O2. Well, in that example, based on the coefficients in the balanced chemical equation, there would not be enough O2 to react with all of the methanol, the CH3OH. 3 moles of O2 is needed, but only 2 moles of O2 is available. So that makes O2 the limiting reactant. Now you might say, well, what number would you pick for an equimolar amount? You could pick pretty much any number, so let's pretend we have 3 moles of each. Now, in this example, looking at the coefficients, only 2 moles of methanol are needed to react with 3 moles of O2, so that means there's going to be 1 mole of extra methanol left over. So the methanol is the excess reactant. That still makes O2 the limiting reactant. So by any definition, O2 is still the limiting reactant. Well, suppose I picked 6 moles of each reactant. How might you process it? Well, I'm going to go ahead and convert each of these amounts into the other reactant. So I'm going to convert from methanol to O2, and then convert from O2 to methanol, and we'll take a look at our results. So I'm using the coefficients from the balanced chemical equation. There are 3 moles of O2 for every 2 moles of methanol. 6 times 3 is 18. 18 divided by 2 is 9. So 9 moles of O2 would be needed to react with 6 moles of methanol. And if we go the other way, now the coefficient ratio would be 2 moles of methanol on the top, 3 moles of O2 on the bottom. 6 times 2 is 12, divided by 3 is 4. So 4 moles of methanol would be needed to react with 6 moles of O2. Well, if I only have 6 moles of O2 available, there is not enough O2 to react completely with 6 moles of methanol. I need 9 moles, but I only have 6. That makes O2 the limiting reactant. Since I only need 4 moles of methanol, but I have 6 moles of methanol available, there's going to be some excess or leftover methanol. That makes methanol the excess reactant, and O2 is the limiting reactant. So there are two strategies to determine the identity of the limiting reactant. The one that I just talked about was the following. If you compare how much reactant is needed with how much reactant is available, you use the stoichiometry calculations to convert the available amount of each reactant into the amount of the other reactant that is needed to react completely with it. And if the amount of a reactant that is needed is greater than the amount that is available, then that reactant is the limiting reactant. But if the amount of a reactant that is needed is less than the amount that is available, then that reactant will be the excess reactant. So the other strategy that you can use to determine the identity of the limiting reactant is to calculate the theoretical yield of product starting from each reactant. Let's take a look. We'll go back to our example here with 6 moles of each reactant, methanol and O2, and we'll convert each of these quantities into product. Now, even though we have more than one product, CO2 and H2O are both products in this reaction, as long as I pick one product and I just stay consistent with my comparison, it doesn't really matter which product you pick. So I'm going to go ahead and pick CO2. So I'm going to convert moles of methanol into moles of CO2, and then I'll convert moles of O2 into moles of CO2, and we'll compare. So using the coefficients from the balanced equation, that would be 2 moles of CO2 produced for every 2 moles of methanol consumed. So 6 times 2 over 2 is still 6. And if I then do the same type of conversion from moles to moles, it would be a ratio of 2 over 3. 2 moles of CO2 are produced for every 3 moles of O2 consumed. 6 times 2 is 12, divided by 3 is 4. Now that I have produced two different numbers, the number that I'm focusing on is going to be the smaller of the two numbers. The theoretical yield limits the amount of product that can be produced. So since 4 moles of CO2 is less than 6 moles of CO2, this tells me that oxygen, O2, is the limiting reactant in this example because it leads to a smaller amount of product in my stoichiometry calculations. If I had chosen to use water, I still would have gotten a smaller amount of water coming from the limiting reactant, the O2. So again, that second strategy is you use your stoichiometry calculations to convert the available amount of each reactant into the amount of product that could be produced from it. And again, if there's more than one product, then you just pick one and be consistent. The reactant that leads to the smaller amount of product is the limiting reactant, and the reactant that leads to the larger amount of product is the excess reactant. All right, moving on to question 3. Hydrogen gas reacts with oxygen gas to form water vapor according to the equation above. For each of the following experiments, identify the limiting reactant and calculate the theoretical yield of water that would be produced in units of moles or grams as shown in the table. So even though we have two different strategies that I've already talked about, where you either convert the reactant into the other reactant or convert each reactant into product, the strategy that I'm going to choose to follow for question 3 is this second strategy, where we calculate the theoretical yield of the product starting from each reactant. So let's take a look at our first example. I have 5.4 moles of H2 and 2.5 moles of O2. I'm going to convert each of them into water to determine both the theoretical yield of water and the identity of the limiting reactant. So to go from hydrogen to water, that would be a ratio of 2 over 2. 2 moles of H2O produced for every 2 moles of H2 consumed. So 5.4 times 2 over 2 is 5.4. And then for the oxygen, that would be a ratio of 2 over 1. 2 moles of water produced for every 1 mole of O2 consumed. So 2.5 times 2 is 5.0. Now, analyzing these two amounts of water, we focus on the smaller number. So the limiting reactant is the one that produces the smaller amount of product. So now I know that O2 is the limiting reactant because in these stoichiometry calculations, it leads to a smaller amount of product, and my theoretical yield of H2O is 5.0 moles. So I fill in that information in the first row of the table, and then we'll move on to experiment 2. In experiment 2, we have 13.2 moles of H2, hydrogen, and we have 6.8 moles of O2, oxygen. Let's convert each reactant into water and see what happens. The same coefficients that we're going to have in this particular calculation we did for experiment 1. So in terms of moles to moles, it's going to be 2 moles of water produced for every 2 moles of H2 consumed. So 13.2 times 2 over 2 is 13.2. And then for the oxygen, it would be a ratio of 2 over 1, 2 moles of H2O produced for every 1 mole of O2 consumed. 6.8 times 2 is 13.6. Now we compare the two amounts. We focus on the smaller of the two amounts, and our conclusion for experiment 2 is the following. Hydrogen is the limiting reactant because it leads to a smaller amount of product in our stoichiometry calculations, and our theoretical yield of water is 13.2 moles. So we filled that information in for experiment 2. Now, on to experiment 3, where instead of having moles as the given amounts of each reactant, we have grams. So it's going to be a longer conversion because we'll have to go from grams to moles, then use the coefficients, and then go from moles back to grams. Let's take a look. 24.5 grams of hydrogen and 201 grams of oxygen. So in our first step, we're going to go from grams to moles using the periodic table. So the molar mass of H2 is 2.016 grams. Then we go from moles of hydrogen to moles of water. You've already seen that ratio before, 2 over 2. And then back to grams. Now you might be thinking, do we really have to go back to grams? Well, it's not necessary to find the identity of the limiting reactant, but we might as well go ahead and do it because then we'll have the actual number of grams that we need for the theoretical yield of water in units of grams. So it's going to be 18.016. That's the molar mass of water. That's how many grams there are in 1 mole of water. So 24.5 divided by 2.016 times 2 over 2 times 18.016. There's my unrounded number for the theoretical yield of water, but we're not done yet. We have to do the same process for O2. We'll first convert grams of O2 into moles. So the molar mass of O2 is 32 grams of O2 on the bottom, 1 mole of O2 on top. Then we use our coefficients, 2 moles of H2O over 1 mole of O2, and then the molar mass of water yet again. So 201 divided by 32 times 2 times 18.016, and then we have our theoretical yield of water coming from oxygen. Remember, we've converted each reactant separately into the possible amount of water that could be produced, but we focus on the smaller of the two amounts in these stoichiometry calculations. So, since the smaller amount of water came from hydrogen, that makes hydrogen the limiting reactant, and the theoretical yield in grams of water would be, rounded off to 3 sig figs, 219 grams of water. All right, we'll do this one more time. This is experiment 4. We have 31.8 grams of hydrogen, 237 grams of oxygen. Same calculation setup as for experiment 3. We go from grams to moles for hydrogen. Then we go from moles of hydrogen to moles of water, and then back to grams of water. So 284.18 is the unrounded answer. We'll repeat the process for oxygen. We go from grams of oxygen to moles, then moles of oxygen to moles of water, and then on to grams of water, and we get 266.86 grams of water. Again, comparing these two separate amounts, we focus on the smaller of the two. So this tells us that oxygen, in this example, is the limiting reactant because it leads to a smaller amount of product. I'll round off my grams of water to 3 sig figs. So I'll say 267 grams of water is my theoretical yield. And again, O2 was the limiting reactant. Okay, this is question 4. The elements potassium and chlorine react to form potassium chloride according to the equation shown above. In a certain experiment, a reaction occurred between 100.0 grams of potassium and 100.0 grams of chlorine, until one of the reactants was completely consumed. Part A. Identify the limiting reactant in this experiment. Justify your choice with both an explanation in words and supporting calculations. You may remember that I showed you two different strategies for identifying the limiting reactant. I'm going to go ahead and show you both of these strategies for question 4, part A. So we'll start with converting each reactant into the other reactant and making a comparison. So I'm going to take 100.0 grams of each reactant and convert each reactant into the other reactant so we can take a look at these numbers. So first I'm going to go from grams of potassium to moles of potassium. 39.10 is the molar mass of potassium. So 39.10 on the bottom, 1 mole on top. Then we go from moles of potassium to moles of chlorine. So based on the coefficients, that would be 1 mole of Cl2 reacting with 2 moles of K. And then on to grams. So the periodic table will give me this information. The molar mass of Cl2 is 70.90 as determined from the information in the periodic table. So if I go 100 divided by 39.1 divided by 2 times 70.9, I get 90.66 grams of chlorine, which is needed to react with 100 grams of potassium. Before I make any conclusions, let me go ahead and run the calculations in the other direction. Let's go from grams of Cl2 to grams of K. So first, grams to moles using the molar mass of Cl2. Then we go from moles of Cl2 to moles of K from the coefficients. And then we go from moles of potassium to grams of potassium from the periodic table. If we do 100 divided by 70.9 times 2 times 39.1, we get 110.3. Now, we've done our calculations. Let's make our conclusions. Which one is the limiting reactant? Well, for chlorine, chlorine is not the limiting reactant. Chlorine is actually the excess reactant. So how can we tell? Well, the amount of chlorine needed, which is 90.66, is less than the amount available, which is 100. So I have 100 grams of chlorine available, but I only need 90.66 grams. That makes chlorine the excess reactant. So potassium is the limiting reactant, and as you can see, the amount of potassium I need, which is 110.3 grams, is greater than the amount available. I only have 100 grams of potassium, so the amount that I need is greater than what's available. That makes potassium the limiting reactant. So just to be complete, I will show you the other method for determining the limiting reactant where we convert each reactant into the product and then compare the amounts. So 100.0 grams of potassium, 100.0 grams of chlorine. Let's convert each of these quantities into the number of grams of potassium chloride, KCl, and then we can compare. So first, grams to moles for potassium. Then we go from moles of potassium to moles of potassium chloride. So that's 2 moles of KCl produced for every 2 moles of K consumed. And the periodic table gives us the information to determine the molar mass of potassium chloride, which turns out to be 74.55 grams of potassium chloride per mole. If we do 100 divided by 39.1 times 2 over 2 times 74.55, 190.66, that's our theoretical yield of KCl starting from potassium. Let's go ahead and repeat that process starting with 100.0 grams of chlorine. First, grams to moles of chlorine using the molar mass of Cl2. Then we go from moles of Cl2 to moles of KCl. That would be a ratio of 2 over 1 from the coefficients. And then multiply by the molar mass of KCl, 74.55. So 100 divided by 70.9 times 2 times 74.55, and we get 210.30 grams of KCl. Remember, we convert each reactant into the product and compare whichever amount of product is the smaller amount that points back to the limiting reactant. So this is just confirmation that potassium is the limiting reactant because it leads to a smaller amount of product. Now that we move on from part A to part B, you can see that part B is going to be a very important number that we just got. in this calculation. Determine the theoretical yield in grams of KCl from this experiment. So the theoretical yield of KCl comes from the limiting reactant. We know that potassium is the limiting reactant in this problem. The theoretical yield always comes from the limiting reactant. So 190.7 is our answer to part B, 190.7 grams of KCl. Moving on to part C, determine the mass in grams of the reactant that is left over, so unreacted at the end of this experiment. Well, if potassium was the limiting reactant, it would all be consumed. But if chlorine is the excess reactant, there's going to be a little bit of chlorine left over at the end. And I'm going to show you two different ways to determine how much chlorine is left over at the end of this experiment. So, one way to figure out how much chlorine is left over is coming from the calculations that I showed you earlier. If only 90.66 grams of chlorine was consumed in this experiment, but 100.0 grams of chlorine was available at the start, then that difference between how much chlorine was available and how much chlorine reacted, that difference is 9.3 when I round off to one decimal place according to the sig fig rules. 9.3 grams of chlorine is left over unreacted at the end. Another way to figure it out is to say, well, we began with 200 grams as the total mass of the reactants, and then our theoretical yield of KCl that came from the limiting reactant was 190.7. So the difference between 200 grams of total reactants and 190.7 grams of theoretical yield of product, that difference between how much we started with in terms of reactants and how many grams of product would be the theoretical yield, that difference is 9.3. So there's 9.3 grams of this excess leftover unreacted chlorine at the end of the experiment. All right, moving on to part D. When this experiment was performed in the laboratory, the actual yield of potassium chloride recovered was equal to 162.1 grams. Calculate the percent yield of potassium chloride. So the actual yield is what we get in the laboratory from doing the experiment. The theoretical yield is what we were supposed to get according to the stoichiometry calculations. So if you get 100% yield from doing the experiment, that means that the actual yield you got in the laboratory was the same as the theoretical yield you were supposed to get from the stoichiometry calculations. Here, 162.1 was the actual yield. We divide that by the theoretical yield, which was 190.7 from part B, and so we end up with 162.1 divided by 190.7, and then times 100 to make that a percent. The correct answer here is 85.0% yield based on the laboratory information and the theoretical yield from the stoichiometry calculations. Now, before we take a look at question 5 in this packet, I'm going to define a quantity that has to do with representing the concentration of a solution, and you'll see in this packet that questions 5, 6, and 7 involve molarity. So let me go ahead and define what molarity is. Molarity will also be defined when we get to Unit 3 in the AP Chemistry course and exam description. So topic 3.7, which is entitled Solutions and Mixtures, has the following essential knowledge statement. Solution composition can be expressed in a variety of ways. Molarity is the most common method used in the laboratory, and molarity, which is abbreviated with a capital M in chemistry, is defined as moles of solute divided by the liters of the solution. You also can see on this slide that I've defined the relationship between liters and milliliters such that 1 liter is equal to 1,000 milliliters in case you need to do any conversions between liters and milliliters or between milliliters and liters. Now I'd like to show you a portion of the AP Chemistry equations and constant sheet. So you can see on the left of this slide, I've highlighted that liter is represented by the symbol capital L. And on the right side of this slide, you can see I've highlighted the metric prefix milli, which is lowercase m, and that would be 1,000th of the base unit. So there are 1,000 tiny milliliters in 1 liter as a definition and a conversion factor. Also, on this next slide is a portion of the AP Chemistry equations and constant sheet. This is the section entitled Gases, Liquids, and Solutions. On the right of this slide, you can see that N, lowercase n, represents the number of moles, and that capital M is an abbreviation for molarity. And then on the left of this slide, near the bottom, you can see that the definition of molarity is moles of solute divided by liters of solution. Okay, now that I've given you that definition of molarity, let's take a look at question 5 in this packet. A student took a 25.0 milliliter sample of a copper nitrate solution of unknown concentration and added an excess amount of 1.0 molar sodium phosphate, causing a precipitate of copper phosphate to form according to the chemical equation shown above. So in the chemical equation shown above, we have solutions of copper nitrate and sodium phosphate, and it produces aqueous sodium nitrate and solid copper phosphate as a precipitate. The solid precipitate was filtered from the solution, dried, and weighed. Part A. The mass of the copper phosphate was recorded as 7.19 grams. Calculate the number of moles of copper phosphate recovered in this experiment. All we have to do is go from grams to moles, but it does require the use of the periodic table to figure out the molar mass of this copper phosphate compound. That's going to be 3 times the atomic mass of copper plus 2 times the atomic mass of phosphorus plus 8 times the atomic mass of oxygen. So grand total, 380.59 grams per mole. We are given 7.19 grams of this precipitate, this copper phosphate. So we're going to convert that from grams to moles, grams on the bottom, 1 mole on top. We do this math. Here's the unrounded answer. Since 7.19 has 3 significant figures, we round off our final answer to 3 significant figures. So that would be 0.0189 moles of copper phosphate. All right, let's move on to part B of this question, in which we're going to need to use the coefficients from the balanced chemical equation, and we're also going to have to do some sort of calculation involving molarity. So part B, calculate the concentration in moles per liter of the copper nitrate solution used in this experiment. So copper phosphate was a product, whereas copper nitrate is a reactant. We'll take our answer to part A, 0.0189 moles of copper phosphate. Again, that was the precipitate. And we have to convert this into moles of copper nitrate using the coefficients in the balanced chemical equation. That's going to be a 3-to-1 ratio based on the coefficients. And if we just did this math by multiplying by 3, this gives us part of what we need to calculate the concentration of the copper nitrate solution. Remember, molarity is moles per liter. So if we go back and read the question more carefully, it said in the beginning that a student took a 25.0 milliliter sample of this copper nitrate solution. And as I mentioned earlier, there are 1,000 milliliters in 1 liter. So to go from milliliters to liters, we're going to divide by 1,000. So 25.0 milliliters is equal to 0.0250 liters. And now that we have both the number of moles of copper nitrate and the volume in liters, we can go ahead and calculate the molarity by simply dividing the number of moles of solute over the number of liters of solution. And if I round that off to 3 significant figures based on the information that we're given, 3 significant figures for our final answer would be 2.27 moles per liter, or if you want to, you could write 2.27 capital M as the abbreviation for molarity. Question 6. Magnesium metal reacts with a solution of nitric acid to produce aqueous magnesium nitrate and hydrogen gas. Part A. write the balanced molecular equation for the reaction that occurs between magnesium and nitric acid. Include the phases of matter symbols for each reactant and product. Well, the first reactant is magnesium metal, which, as we are told, is written as Mg and then S for solid. The second reactant is nitric acid, which we are told is written as HNO3, and that's a solution, that's aqueous. The first product is magnesium nitrate. So to write that formula correctly, we should pay attention to the formula and the charge for the positive ion, which would be magnesium 2+. Magnesium is located in group 2, so it has a charge of 2+. And then nitrate is a polyatomic ion, which has the formula NO3 with a charge of -1. Since the charge on nitrate is only -1, it doesn't balance the charge on magnesium. So we need 2 nitrate ions for every 1 magnesium ion. Therefore, that formula should be written as Mg and then NO3 in parentheses with a 2 on the outside. Again, that's aqueous magnesium nitrate. The last product is hydrogen gas, and since hydrogen is a diatomic element, we write that as H2, again, G for gas. This equation is almost perfect. Everything looks good on both the left and the right. All we have to do is balance the equation, so we have to put a 2 as the coefficient in front of the nitric acid. So this is our correct answer to part A. All right, let's move on to part B. Part B says to write the balanced complete ionic equation for the reaction that occurs between magnesium and nitric acid. So here is our molecular equation from part A. And you may recall from topic 4.2, which was on net ionic equations in an earlier video, that we have to decide whether we split something up or leave it together in terms of electrolyte or non-electrolyte. We are told that nitric acid, HNO3, is classified as a strong acid, and therefore in solution it is completely ionized into the ions H+ and NO3-. So when we write the complete ionic equation, we're going to split up HNO3 into the separate ions. You have already learned that when an ionic compound that contains usually a metal and a nonmetal, or more generally a cation and an anion, when an ionic compound is dissolved in water, it also is split up into separate ions. So to write the complete ionic equation, we're going to split up the nitric acid into H+ and NO3-, and we're going to split up the magnesium nitrate into Mg2+ and NO3-. Don't forget to use the coefficient on the left. So we have 2 H+ ions and 2 NO3- ions. And on the right, don't forget that the subscript 2 outside the parentheses now becomes a coefficient. So there's 1 magnesium 2+ ion, and there's 2 nitrate ions. Again, don't forget to include the charge. So this equation, this complete ionic equation, is now correctly balanced in terms of both atoms and charge. As we move from part B to part C, we're going to take our complete ionic equation and cross off the spectator ions on both sides. This will give us the net ionic equation. So once we cross off the nitrate ions on the left and on the right, what we have left now is the net ionic equation. So magnesium plus 2 H+ ions produces an Mg2+ ion and hydrogen gas. Everything is still balanced in terms of both atoms and charge. All right, let's move on to part D of this question. It says calculate the mass of magnesium metal that is required to react completely with 50.0 milliliters of 0.625 molar nitric acid. So 0.625 and then capital M, that means molarity. That means that there are 0.625 moles of nitric acid for every 1 liter of solution. So when you write the molarity with a top and a bottom in terms of number and unit, you can think of it as a conversion factor. So we could replace 1 liter of solution with 1,000 milliliters of solution, or we could write either of these conversion factors upside down. So it might be helpful to take the molarity and treat it as a conversion factor with moles of solute on one side of the line and then volume of solution on the other side of the line. That way you can think of it as a conversion factor that can be useful in your stoichiometry calculations. We're going to start with 50.0 milliliters of this solution, and we're going to eventually end up with grams of magnesium. So the first step might be to go from milliliters to liters. So we divide by 1,000 to do that. Then we could go from liters of solution to moles of nitric acid. So 0.625 moles of nitric acid per liter. Now, to go from moles of one chemical to moles of another, in this case magnesium, let's remember the answer to part A of this question. So here was the balanced equation that you wrote earlier in part A, and there's 1 mole of magnesium for every 2 moles of nitric acid. Now we have to get to grams of magnesium. Let's use the periodic table to do that. So the periodic table tells us that there's 24.30 grams of magnesium per mole. So I've started with milliliters of solution, and then in 1, 2, 3, 4 conversion factors, I finish with grams of magnesium. You could just do the math in your head of do 50 divided by 1,000, but remember that's 3 significant figures, 50.0. So if you're going to write that volume in liters, don't just write 0.05, it's actually 0.0500, so you preserve 3 significant figures for the volume of the solution. And yes, you could go from liters to moles of nitric acid, and then convert that to moles of magnesium, and then to grams of magnesium. So if you do this math, your answer is 0.37969. Let's go ahead and round off our answer based on the number of significant figures in the given amounts, the measurements. So 50.0 has 3 significant figures. 0.625 also has 3 significant figures. So we'll round off our answer to 3 significant figures, 0.380 grams of magnesium. So that is our answer to part D. Question 7. Aluminum metal reacts with a solution of sulfuric acid to produce aqueous aluminum sulfate and hydrogen gas. Part A, write the balanced molecular equation for the reaction that occurs between aluminum and sulfuric acid. Include the phases of matter symbols. So for the reactants, we know that the reactants are aluminum, so Al, and that's a solid. Sulfuric acid, H2SO4, and that is a solution, so it's aqueous. Then we have aqueous aluminum sulfate. So if you're not sure how to write the formula for aluminum sulfate, break it down into the cation, which is aluminum, and then the anion, which is sulfate. So the formula and charge for the aluminum ion would be Al 3+, based on where we find aluminum on the periodic table. That pattern gives aluminum a charge of 3+. Now sulfate is a polyatomic ion, and it happens to have the formula SO4, and the charge is 2-. So we don't have a balanced formula with just 1 aluminum and 1 sulfate. We need a total charge of 0. So we need there to be a total of 2 aluminum ions, so +6, and then 3 sulfate ions, -6. We write the formula as Al2 and then SO4 in parentheses with a 3 on the outside. Again, that was aqueous, plus hydrogen gas, that would be diatomic hydrogen, so H2, and then G for gas. This is the unbalanced equation. To balance the equation, we need 2 aluminums on the left, so there's a coefficient of 2, and then we need 3 SO4s on the left, so a coefficient of 3, and now we need 6 hydrogen atoms on the right, so a 3 right there. So that is our answer for part A. That's the balanced molecular equation. Let's move on to part B. Part B says, in a certain experiment, 15.3 grams of aluminum is reacted with a solution of 6.00 molar sulfuric acid. Part I, calculate the minimum volume in milliliters of a 6.00 molar solution of sulfuric acid that is required to react completely with 15.3 grams of aluminum in this experiment. Let's begin with the mass of aluminum. So 15.3 grams of aluminum. A good first step to start off a stoichiometry problem, if you're given grams, is to go from grams to moles. Let's use the periodic table to do that. So grams of aluminum on the bottom, and then 1 mole of aluminum on top. 26.98 is the molar mass of aluminum. Now we have to go from moles of aluminum to moles of sulfuric acid. So if you recall the balanced equation that we wrote in part A, which looks like this, there's 3 moles of sulfuric acid for every 2 moles of aluminum. So we can do that conversion factor, putting moles of sulfuric acid on the top and moles of aluminum on the bottom. Now, you might think that the next step is to go from moles to grams. We've seen that pattern before. But in this case, they want the answer to be the volume of the solution. As I mentioned earlier in the video, if we take that capital M, which represents the molarity, and we unpack it and turn it into a conversion factor, that would be 6.00 moles of sulfuric acid for every 1 liter of solution. 6.00 moles of sulfuric acid would go on the bottom, and then 1 liter of solution would go on top. Now at this point, if we stop right now and do this calculation, our answer would be in liters of solution. Since they want the volume in milliliters, let's just go ahead and replace 1 liter of solution with 1,000 milliliters of solution. So the math involved would be 15.3 divided by 26.98 times 3 divided by 2 times 1,000 and then divided by 6.00. And we get an unrounded answer of 141.77, since the 15.3 grams has 3 significant figures, and then the molarity also has 3 significant figures, 6.00. Let's go ahead and round off our answer to 3 significant figures. That would be 142 milliliters of solution. All right, this is part II. It says, assuming that 15.3 grams of aluminum reacts completely with an excess amount of sulfuric acid, calculate the theoretical yield of hydrogen gas produced in this experiment. So this will be a 3-step conversion. We're going to start with grams of aluminum and then go all the way to grams of hydrogen. The reason why it's a 3-step conversion is that first we go from grams of aluminum to moles of aluminum using the periodic table. Then we go from moles of aluminum to moles of hydrogen using the coefficients in the balanced chemical equation. So 3 moles of hydrogen are produced for every 2 moles of aluminum that are consumed. And then we finish off with another step, which is the periodic table. The molar mass of hydrogen is 2.016 from the information in the periodic table. So 15.3 divided by 26.98 times 3 divided by 2 times 2.016 gives us an unrounded answer of 1.71487. And based on the 15.3, which is the measurement, it has 3 significant figures. Let's round off our final answer to 3 significant figures. So 1.71 grams of hydrogen. All right, that was II. Let's move on to part III. It says, when this experiment was performed in the laboratory, the actual yield. So again, we just got the theoretical yield, which was 1.71. The actual yield of hydrogen was 1.35 grams. Calculate the percent yield of hydrogen. So take the actual yield, 1.35 grams, divided by the theoretical yield, which is 1.71 grams, and then times 100 to convert that to a percent. And our answer for part III is 78.9% yield. Question 8. This question involves both stoichiometry and the properties of gases. The reaction between nitrogen monoxide, NO, and oxygen, O2, to produce nitrogen dioxide, NO2, in a rigid reaction vessel is represented in the diagram above. The pressure inside the container is recorded using a pressure gauge. Part A. Write the balanced molecular equation for the reaction that occurs between NO and O2 to produce NO2. So our reactants are NO plus O2, and our product is NO2. To balance this equation, we need to get more oxygens on the right. So I'll put a 2 in front of the NO2, And now I need another nitrogen on the left, so I'll put a 2 in front of the NO. And if I look at this equation, it is now balanced. There are a total of 2 nitrogen atoms and 4 oxygen atoms on both sides of the equation. So that is the correct answer for part A. Now, with respect to this pressure inside the container recorded using a pressure gauge, let's take a look at part B. Which of the following statements correctly predicts the change in pressure as this reaction goes to completion at constant temperature and provides the correct explanation? So we have 4 choices. The first choice says the pressure will increase. The second and the third choices say that the pressure will decrease. And then the last choice says the pressure will not change. So you may have heard of this equation before, but if not, that's okay. This is called the ideal gas equation. So PV equals nRT. And the letters P and V and N and T represent different properties or variables that we use to describe gases. So P stands for pressure, V stands for volume, N stands for the number of moles or the number of particles of gas, and then T stands for the temperature. It says that this reaction occurs at constant temperature, and as you can see, it is a rigid reaction vessel. The volume of the vessel is not changing. So the volume is not changing, and the temperature is not changing. So what is this about? It's about the pressure and the number of moles. Take a close look to see if the number of moles of gas is changing as this reaction proceeds. Well, on the left, we have 2 moles of NO and 1 mole of O2. That's a total of 3 moles of gas for the reactants. But on the right, we have 2 moles of NO2. That's 2 moles of gas. So the number of moles of gas is actually changing as this reaction proceeds. You can also see in the particle diagram, we go from 12 molecules that are depicted in the particle diagram on the left, and then we have 8 molecules in the particle diagram on the right. So what happens when the number of moles or the number of molecules of gas decreases? Well, gas pressure is caused by collisions between the gas particles and the container walls. Focus on the change in the number of molecules of gas as the reaction proceeds. If the number of molecules of gas is decreasing, that will cause the pressure inside the container to decrease. So the correct answer is the second choice. The pressure will decrease because there are fewer moles of product than reactants. Question 9. This question also involves stoichiometry and the properties of gases. The reaction represented above goes essentially to completion. The reaction takes place in a rigid reaction vessel that is initially at 600 Kelvin. A sample of CH3OH gas is placed in the previously evacuated reaction vessel with an initial pressure of 1.74 atmospheres at 600 Kelvin. So the 1.74 atmospheres is the pressure of just the reactant, the CH3OH. Calculate the final pressure in the reaction vessel after the reaction is complete and the contents of the vessel are returned to a temperature of 600 Kelvin. In the previous problem, in question 8, I said that gas pressure is caused by the collisions between gas particles and the container walls. What happens in this particular reaction is we go from 1 mole of gas for the reactants to 3 moles of gas for the products. So if we are increasing the number of particles of gas by a factor of 3, that means we're going to increase the pressure in the container by a factor of 3. So the final pressure in the reaction vessel, when this reaction is complete, will be 3 times as much as the original pressure before the reaction occurred. So if 1.74 atmospheres was the initial pressure, the final pressure should be 1.74 times 3, and our answer to number 9 is 5.22 atmospheres. All right, moving on to a new topic. This is topic 4.6, Introduction to Titration. Here is an essential knowledge statement from the AP Chemistry course and exam description. Titrations may be used to determine the concentration of an analyte in solution. The titrant has a known concentration of a species that reacts specifically and quantitatively with the analyte. The equivalence point of the titration occurs when the analyte is totally consumed by the reacting species in the titrant. The equivalence point is often indicated by a change in a property, such as color, that occurs when the equivalence point is reached. This observable event is called the endpoint of the titration. Now, I know that was a lot of information to process, so let me go ahead and give you a list of details related to a titration experiment. A standard solution is used containing a known amount of a certain reactant. An analyte solution is used containing an unknown amount of another reactant. A balanced chemical equation is needed to describe the reaction that occurs when the two solutions are combined. An acid-base reaction is a common scenario for a titration experiment. However, a titration can also be performed with a precipitation reaction or an oxidation-reduction reaction. A buret, which is that long piece of glassware you see in the diagram on the right, is filled with a solution containing one of the reactants. The buret normally has graduation marks that are in 0.1 milliliter increments. The volume measurement is normally estimated to the nearest 0.01 milliliters. The solution in the buret is called the titrant, and it is added in small amounts to the other solution, which is usually in an Erlenmeyer flask. The flask is swirled frequently to mix the contents during the titration. The equivalence point is reached when one reactant has completely reacted with the other reactant according to the stoichiometry of the chemical equation. An indicator can be used that will change color to give a signal when the equivalence point is reached, and you'll often see in acid-base reactions they will use an acid-base indicator that changes color. In this example, you see a little flash of pink that represents an acid-base indicator known as phenolphthalein. The endpoint is an observation that indicates when to stop adding the titrant, and then the final volume on the buret should be recorded. In an acid-base titration, the pH of the solution in the flask can be monitored during the experiment. The pH data can be used to create a titration curve. The pH is usually plotted on the y-axis, and the volume of the titrant added is plotted on the x-axis. The equivalence point of the acid-base titration occurs when there is a rapid change in pH. Question 10. The pH curve from a titration experiment is shown at right. Part A, determine the volume of 0.24 molar sodium hydroxide that is required to reach the equivalence point in this titration. So what feature of this titration curve are we really looking for to figure out the equivalence point? Well, the last detail that I had mentioned is that the equivalence point of an acid-base titration occurs when there is a rapid change in pH. So where do we see a rapid change in pH on this curve? Well, there's a sharp increase right here at a volume of 35 milliliters. So the answer to part A is that at 35 milliliters of this particular titrant that was added, that's when the equivalence point occurs. That's the rapid change in pH. For part B, calculate the number of moles of sodium hydroxide that is required to reach the equivalence point. Well, we know the volume and we know the molarity, so we can figure out the moles. I'm going to go ahead and convert 35 milliliters into liters. So you divide by 1,000 to go from milliliters to liters. That would be 0.035 liters of solution. And then 0.24 is the molarity. That would be 0.24 moles of sodium hydroxide for every 1 liter of solution. So if we do this math, then our answer will be in units of moles of sodium hydroxide. And that would be, you could write this in regular notation. You can say 0.0084 moles of sodium hydroxide, or you could express this in scientific notation, which would be 8.4 times 10 to the minus 3 moles of sodium hydroxide. Question 11. A student performs an experiment in which a solution of potassium hydroxide, KOH, is titrated with a solution of sulfuric acid, H2SO4. The purpose of the experiment is to determine the concentration of KOH in the solution. Part A. Write the balanced molecular equation for the reaction that occurs between solutions of sulfuric acid and potassium hydroxide. Include the phases of matter symbols. So sulfuric acid is H2SO4, and that's aqueous. Potassium hydroxide is KOH, and that's also aqueous. The products of the reaction are water and aqueous potassium sulfate. If you're not sure how to write the formula of potassium sulfate, think about the symbol and the charge of the cation and the anion and then put them together. So potassium would be K with a charge of +1. Sulfate is a polyatomic ion, that's SO4 with a charge of 2-. So to balance out the charges in this formula, we need 2 potassiums for every 1 sulfate ion. So the formula is K2SO4, and again, that's aqueous. Now we have to balance the equation, so we need 2 potassium atoms on the left, and then we have a total of 4 hydrogen atoms on the left, so we need 4 hydrogen atoms on the right. So again, the coefficients are 1, 2, 2, and 1 from left to right. Okay, that is the correct answer to part A. Let's move on to part B. All right, part B says a student prepares a solution of sulfuric acid by adding 25.0 milliliters of 3.50 molar sulfuric acid to a volumetric flask and diluting the solution to a final volume of 500.0 milliliters. Calculate the concentration in moles per liter of sulfuric acid in the diluted solution in the volumetric flask. So initially they had 25.0 milliliters of 3.50 molar sulfuric acid. Let's turn that volume from milliliters into liters. So I'm going to go ahead and divide by 1,000. So 25.0 divided by 1,000 is 0.0250 liters. Remember that molarity is moles per liter. That's 3.50 moles of sulfuric acid for every 1 liter of solution. So multiply those numbers together and I get 0.875. That's the number of moles of sulfuric acid. And now it's been diluted to 500.0 milliliters. Let me turn that volume into liters. Molarity is moles over liters. So 0.0875 moles divided by a total volume of 0.5000 liters. If I do that math, moles over liters, I get an answer of 0.175 moles per liter. So that is the concentration of sulfuric acid in the diluted solution in the volumetric flask. All right, before I move on to part C, let me show you another way to get the correct answer to part B using some algebra. This equation might be familiar to some of you. M1V1 equals M2V2, or you could write this as MCVC equals MDVD, where C stands for the concentrated solution and D stands for the dilute solution. M is the molarity, V is the volume. So in this particular problem, in part B, the molarity of the concentrated solution was 3.50. The volume of the concentrated solution that was used was 25.0 milliliters, or 0.0250 liters. The molarity of the dilute solution is, we don't know yet, we're trying to find that in this problem. And then the volume, the final volume of the dilute solution was 500.0 milliliters, or 0.5000 liters. If you look at this algebraic equation, we can go ahead and just solve for the variable, which is the molarity of the dilute solution. And on the left and on the right, as long as those two volume values on opposite sides of the equation are in the same unit, they could be in either liters or milliliters. You would get the same answer either way, as long as you're consistent with your units for volume on both sides of the equation. So to do this algebra, it would be solving for the molarity of the dilute solution, 3.5 times 25 divided by 500, we get the answer that I already mentioned. The molarity of the dilute solution is 0.175 moles per liter. Okay, let's go ahead and move on to part C. In order to determine the concentration of a potassium hydroxide solution, a titration experiment is performed. A clean buret is filled with the sulfuric acid solution that was prepared in the procedure described in Part B. A 50.0 milliliter sample of potassium hydroxide is added to a clean Erlenmeyer flask. The pH is monitored during the titration experiment, and the experimental results are plotted in the graph shown at right. Part C, determine the volume of sulfuric acid that is required to reach the equivalence point in this titration. So on this graph, where do we see a rapid change in pH? That would be right here at 30 milliliters. So on the x-axis, the volume of sulfuric acid added would be 30 milliliters. Part D says to calculate the concentration in moles per liter of the potassium hydroxide solution used in this experiment. So the potassium hydroxide solution, that's the one that's in the flask, whereas the sulfuric acid, that was in the buret. Let's take 30 milliliters, and let's divide that value by 1,000. So 30 divided by 1,000 would be 0.030. So now we have our volume of solution in liters. What's the concentration of sulfuric acid? Well, that was our answer to Part B. So the concentration of sulfuric acid was 0.175 moles per liter. Again, that was our answer to Part B. Now we have to go from moles of sulfuric acid to moles of potassium hydroxide. So we need the balanced equation, which was written in Part A of this question. So here's the balanced equation from Part A, and as you can see from the coefficients, there are 2 moles of potassium hydroxide for every 1 mole of sulfuric acid. If we do this math, 0.03 times 0.175 times 2, that gives us the number of moles of potassium hydroxide. But the question says, what's the concentration, which is moles per liter? So what was the volume of the potassium hydroxide that was used in this experiment? Well, the volume was 50.0 milliliters that was put into the Erlenmeyer flask. If molarity is moles divided by liters, let's take that 0.0105 moles of potassium hydroxide and divide by the volume in liters. So 50 divided by 1,000 would be 0.0500 moles over liters, 0.0105 divided by 0.0500, and we get a final answer of 0.21 moles per liter. The reason why I rounded off my final answer to 2 significant figures is because I was limited by the volume of the solution of sulfuric acid in Part C. Since the volume 30 milliliters has only 2 significant figures, I rounded off my final answer to 2 significant figures. The following is a common procedure used to prepare a buret. First, you rinse the buret with water. Add a small amount of distilled water to the buret. Hold the buret horizontally and rotate it so that the interior surfaces are rinsed with water. Drain the buret. Repeat this step 3 times. Then you rinse the buret with standard solution. So a small amount of standard solution is added to the buret. Hold the buret horizontally and rotate it so that the interior surfaces are rinsed with the standard solution. Drain the buret. Repeat this step 3 times. And then you load the buret with the standard solution. So you fill the buret with the standard solution, allow some of the standard solution to drain out of the bottom of the buret. The buret tip should be filled with liquid and no air bubbles should be visible in the buret tip. If you watch the video, and I will include a link to this video in the video description, you can see a procedure for how to prepare a buret. All right, moving on to question 12. Vinegar is a solution that contains acetic acid, HC2H3O2. Acetic acid reacts with sodium hydroxide according to the equation above. A student is given a sample of vinegar and asked to do a titration experiment in order to determine the concentration of acetic acid in the vinegar solution. The student uses a standard solution of sodium hydroxide, a buret, an Erlenmeyer flask, an appropriate acid-base indicator to signal the endpoint, and other laboratory equipment necessary for the titration. If you want to watch this video about the titration of vinegar, you can take a look at the link which I will post in the video description. You can watch that particular experiment for the titration of vinegar. All right, moving on to part A, it says a sample of 25.0 milliliters of vinegar is added to the flask in the titration experiment. The images below show the buret before the titration begins on the left and at the end point on the right. In the table below, record the initial and final buret readings and the calculated value for the volume of sodium hydroxide required to reach the endpoint. So what is the initial buret reading? When you read the volume on a buret, we read it from top to bottom. So you can see there's a 5 and there's a 6. So the volume would be recorded. It's somewhere between 5 and 6 milliliters. If we look closely, the bottom of the meniscus is somewhere between 5.6 and 5.7 on the buret. So we estimate to the nearest 100th place. I'm going to go ahead and estimate that it's 5.65 milliliters, again, based on the bottom of the meniscus. Now, on the final buret reading, it's going to be somewhere between 37 and 38 milliliters. But unlike the initial buret reading where it was actually in between two hash marks, this one looks like it's right on the line at 37.3. The bottom of the meniscus is right there on the line at 37.3, but we still have to estimate the final digit to the 100th place. So I would go ahead and add a 0 to indicate the precision that it's right there on the line. So 37.30 is how I would make that volume measurement. Now, to figure out the volume of sodium hydroxide that was required to reach the endpoint, it's just the difference between the initial and the final reading. So 37.30 minus 5.65 gives me a volume of 31.65 milliliters of this sodium hydroxide solution. Part B. Based on the given information and your answer to Part A, calculate the concentration in moles per liter of acetic acid in the 25.0 milliliter sample of vinegar. So what do we know from Part A? We know the volume of sodium hydroxide is 31.65 milliliters. That was based on the buret calculations. We also know from the information in the table that the concentration of sodium hydroxide is 0.665 moles per liter. Another thing that we know is the balanced chemical equation, which is helpful because we can see that the relationship between acetic acid and sodium hydroxide is a 1-to-1 mole ratio based on the coefficients. So I'm going to start with the volume from Part A. 31.65 milliliters. I'm going to turn that into liters. So divide that number by 1,000. 31.65 divided by 1,000 is 0.03165 liters of sodium hydroxide. Let me go ahead and use molarity as a conversion factor. 0.665 moles of sodium hydroxide for every 1 liter of solution. And then to get to acetic acid, it's going to be based on the coefficients, but that's a 1-to-1 mole ratio. There's 1 mole of acetic acid for every 1 mole of sodium hydroxide. If I do the following calculation, I get 0.02105, at least for right now. I'm not going to round off that number too much yet. That's my moles of acetic acid. But they want the concentration. They want moles per liter. So to get moles per liter, I've got to take that number of moles of acetic acid and divide by the volume. So 25.0 milliliters, when I convert that to liters, is 0.0250 liters of solution for the vinegar. So moles over liters, if I do this math, my final answer to Part B is 0.842 moles per liter. That's the concentration of acetic acid in the vinegar sample. And I rounded off my final answer to 3 significant figures because 25.0 milliliters also has 3 significant figures. Part C. The student performed a second trial of the titration using a 25.0 milliliter sample of vinegar and a standard solution of 0.665 molar sodium hydroxide. The student made the following mistake when they prepared the buret. After rinsing the buret with distilled water, the student did not rinse the buret with the standard sodium hydroxide solution before filling the buret with 0.665 molar sodium hydroxide. Based on this mistake, do you predict that the calculated value for the concentration of acetic acid in trial 2 should be less than, greater than, or the same as the value obtained in trial 1? Justify your answer. So here was their mistake. They had a buret which was rinsed with water. Now, after the rinsing with water, there should be a few drops of water that cling to the inside of the buret. But instead of rinsing the buret with the standard sodium hydroxide solution, they just filled the buret with the standard solution of sodium hydroxide. So because of those drops of water, it's going to cause the concentration of sodium hydroxide to go down a little bit. It's going to be diluted with those drops of water. So the concentration of the sodium hydroxide in the buret is going to be too low because it's been diluted with water. Now, what effect is that going to have on the titration experiment? Well, with a slightly lower concentration of sodium hydroxide, then it's going to require a little bit larger volume of that solution to reach the endpoint. So the volume of sodium hydroxide would be too high based on that mistake. And then when you calculate the number of moles of sodium hydroxide, that value would be too high because you're doing volume times molarity to get moles. And if your moles of sodium hydroxide is too high, then your moles of acetic acid would also be too high based on that 1-to-1 ratio. So the answer is that the calculated value for the concentration of acetic acid in trial 2 should be greater than the value obtained for trial 1. Question 13. A student obtains a solution that contains an unknown concentration of iron 2+ ions. The student performs a titration experiment in order to determine the concentration of iron 2+ in the solution. The titration involves a chemical reaction between permanganate, which is MnO4-, and iron 2+, according to the equation above. The buret is filled with a standard solution of 0.0425 molar potassium permanganate. A sample of the iron 2+ solution is added to an Erlenmeyer flask. Observations from the experiment are recorded in the data table below. Part A. Use the information in the data table to calculate the missing information in the last row. So we're looking for the volume of the titrant, the potassium permanganate, that was required to reach the endpoint. And this is based on the buret readings, the difference between the final buret reading and the initial buret reading. So for trial 1, that difference is 19.87 minus 2.45. That's a difference of 17.42 milliliters. In trial 2, it's based on a difference of 46.34 minus 19.87, so that's 26.47 milliliters. Now, we know the volume of titrant that was used in trial 1 and trial 2. Let's move on to part B. Part B. Use the information in the data table and the balanced chemical equation to calculate the concentration of iron 2+ for both trial 1 and trial 2. Let's go ahead and start with trial 1. It says that 17.42 milliliters of this potassium permanganate solution was used. Let me convert from milliliters to liters by dividing by 1,000. So that becomes 0.01742 liters of potassium permanganate. Now I'm going to convert from liters to moles using molarity as a conversion factor. So it says in the table that the concentration of permanganate is 0.0425. That's 0.0425 moles of potassium permanganate for every 1 liter of solution. In the balanced chemical equation on the left, we see not potassium permanganate, but just MnO4-, the permanganate ion. So I'm going to go ahead and show you that there is 1 mole of the permanganate ion for every 1 mole of potassium permanganate. And now I can use the 1:5 ratio based on the coefficients to convert from permanganate to iron. So there's 5 moles of the iron 2+ ion for every 1 mole of permanganate from the balanced equation. If I run this particular calculation that's set up, I'm going to calculate the number of moles of iron 2+ that was consumed in trial 1. And so when I do that math, I get 0.0037018, and I'm not going to round that number off yet because I'm not done with my calculation. They want the concentration. Concentration is moles per liter. So I have the moles. My volume of solution in trial 1 is 10.0 milliliters, or 0.0100 liters of solution. So now when I do this math of moles of iron divided by liters of solution, I get my answer for trial 1. The concentration of iron 2+ is equal to, when I round it off to 3 significant figures, 0.370 moles per liter. Now we'll go ahead and run the calculation for trial 2. So it's very similar. We start with the volume of the titrant, and I converted that from milliliters to liters by dividing by 1,000. I used the molarity as a conversion factor to go from liters of solution to moles of potassium permanganate. There's 1 mole of the permanganate ion for every 1 mole of potassium permanganate. There's that 5:1 ratio from the coefficients, so 5 moles of iron 2+ for every 1 mole of permanganate. If I run those calculations and do that math, I get the number of moles of iron 2+ that was consumed in trial 2. Molarity is moles over liters. So my volume in trial 2 of the iron solution was actually 15.0 milliliters, or 0.0150 liters of solution. So moles of iron divided by liters of solution. And if I do that calculation, rounding off to 3 significant figures, I get 0.375 moles per liter. So my answer to part B, the concentration of iron for trial 1 and trial 2, 0.370 and 0.375. So as we can see from the data for trial 1 and trial 2, the concentration of iron 2+, those values are pretty similar to each other, but the value for trial 2 is slightly higher than the value for trial 1. Let's go ahead and talk about part C. Part C, during the second trial, the student accidentally added extra titrant past the endpoint, so that more potassium permanganate solution was added to the flask than was needed to reach the endpoint. Would this error explain the difference in the calculated values of the concentration of iron 2+ obtained in part B? Justify your answer. So this mistake would cause the volume of potassium permanganate solution to be too high because an extra amount of the titrant was mistakenly added by the student in trial 2. And to get the number of moles of permanganate, you do volume times molarity. So the calculated amount of moles of permanganate would be too high in trial 2. And then when they convert from moles of permanganate to moles of iron, it would cause the calculated amount of moles of iron to be too high in trial 2. So the calculated value for the concentration of iron 2+ in trial 2 would be greater than the value obtained in trial 1. So yes, this error would explain the difference in the calculated values of concentration of iron 2+, because the number for trial 2 is a little bit higher than the number for trial 1. Question 14. Potassium hydrogen phthalate, KC8H5O4, reacts with potassium hydroxide according to the equation above. A student performs a titration experiment in which a buret is filled with a solution of potassium hydroxide of unknown concentration. A sample of 1.25 grams of solid potassium hydrogen phthalate is added to a clean Erlenmeyer flask and dissolved in 50.0 milliliters of water. A few drops of an acid-base indicator is added to the flask to ensure visual detection of the endpoint. Part A. calculate the number of moles of potassium hydrogen phthalate used in this titration experiment. So we know that there's 1.25 grams. We have to convert from grams to moles. Let's calculate the molar mass of KC8H5O4. So if we look at the periodic table and we use the atomic mass values for potassium, carbon, hydrogen, oxygen, we get a molar mass of 204.22 grams per mole. Let's take the mass we're given in this problem, 1.25 grams of this chemical. So times 1 mole over the molar mass. Do that math and we get the number of moles, which is 0.061209. Let's round this off to 3 significant figures based on the 1.25, which has 3 sig figs. So 0.00612, or you could write this in scientific notation, 6.12 times 10 to the negative third moles of this potassium hydrogen phthalate. In part B, it says it is determined that 18.75 milliliters of potassium hydroxide is required to reach the endpoint. Calculate the concentration of the potassium hydroxide solution used in this titration experiment. So what we know so far from part A is that we have 0.00612 moles of potassium hydrogen phthalate. We have a balanced chemical equation with coefficients of 1 for the reactants, so that tells us that there's 1 mole of potassium hydroxide for every 1 mole of potassium hydrogen phthalate. So now we know the moles of potassium hydroxide, which is 0.00612. Molarity is moles over liters. And we have a volume in this problem. 18.75 milliliters of the solution was used to reach the endpoint. So we're going to take moles of potassium hydroxide divided by the volume in liters. So not 18.75, but rather 18.75 divided by 1,000. So 0.01875 liters. Moles divided by liters should give us the concentration. And when we do that math, and we round off our answer to 3 significant figures, because the 1.25 is our limiting factor that has 3 sig figs, we get 0.326 moles per liter. That's the concentration of potassium hydroxide that was used in this experiment. In part C, it says the student performed a second trial of the titration. A sample of 1.25 grams of potassium hydrogen phthalate is added to a clean Erlenmeyer flask and dissolved in 30.0 milliliters of water instead of 50.0 milliliters of water as in trial 1. A few drops of an acid-base indicator is added to the flask to ensure visual detection of the endpoint. Do you predict that the calculated value for the concentration of potassium hydroxide in trial 2 should be less than, greater than, or the same as the value obtained in trial 1? Justify your answer. So in trial 1, we calculated the number of moles of potassium hydrogen phthalate by converting grams to moles. We didn't use the 50.0 milliliters of water in our calculations at all. So the value for the number of moles of potassium hydrogen phthalate comes from the mass of the solid. It is not related to the volume of water added to the flask. So whether we add 30 or 40 or 50 milliliters of water to the flask, it shouldn't make a difference at all. The value for the number of moles of potassium hydrogen phthalate comes from the mass of the solid, which is the same for both trials. It's 1.25 grams. So the number of moles of potassium hydrogen phthalate should be the same for both trials. And this indicator will change color when all the moles of potassium hydrogen phthalate has reacted. The number of moles of potassium hydroxide should be the same for both trials, so the calculated value for the concentration of potassium hydroxide in trial 2 should be the same as the value obtained in trial 1. All right, well, that represents the end of this particular question. It's also the last question in the packet. So this is the end of the video. I hope that these answers and explanations were helpful. Thanks for watching.